So, Mr. Algebra, what do you get?
That's Dr. Algebra. I did not spend 12 years in evil algebra school to be called Mr. Algebra. Okay.
My apologies.
All right. Well, I think there's actually only one answer here, and that answer is 2.
All right, which one is that?
Both of them.
So there's 2 2s?
2 2s.
How do you get that? Okay, so you squared both sides, and that causes the epsilon to be squared. It gets rid of all the square roots. Then, but then we get it, because we squared both sides, we get it divided by 4 over here, which ultimately is going to meet up with the half over here, and we're going to get a 2. Yeah, that's right. Very good.
And thus more proof that every single thing in computer science gets generalized once you have 2 of them.
2 is important in computer science. So let's see what we actually get here. What we're saying is that if we sample an arm at least this many times, 2 times 1 over epsilon squared. Now, 1 over epsilon squared is polynomial in 1 over epsilon, 1 over delta, and k, times the logarithm of 2k over delta. So again, this quantity here is polynomial in k and 1 over delta, and we're logging it. And that gives us a count that if we do that enough times, we're actually going to be sufficiently certain that we're sufficiently close that choosing the maximum arm is going to be a good idea. And it's interesting to note here that the dependence on the certainty parameter is actually quite weak, right? So it's 1 over delta, and it's stuffed into the log. So this is having not a huge impact. But the dependence on the epsilon parameter is actually quite profound. It's 1 over epsilon. So if we're talking about like 0.00001, that's like, I don't know, 1,000 or 10,000 or something. And then we square that. And so we could actually need a ton of samples if we want to be very, very sure that we're very, very close. In fact, even if we want to be moderately sure that we're very, very close, there's just this big dependence on the epsilon.
So what you're saying is that the hard part is getting very, very close, not being certain how close you are.
It looks that way. Yeah, that's what this equation is telling us.
So we've said this before, since it's all hufting here and hufting there and hufting all the way down, that you're going to get stuff that looks like pack bounds. But this looks really similar to the pack bound for agnostic learning, right? There's like a 1 over epsilon squared and a natural log of delta in there, 1 over delta or something in there.
Yeah, and it uses a union bound too. It uses the union bound and the hufting bound, just like we just did. But I mean, it's not exactly the same thing, but you're right. It has a very similar flavor.
I look at this and I just think one of these looks a lot like, this says something about hypothesis space. And the other is about the error. And it just feels like there's a connection there.
That there's a sense in which you can think about the payoffs of the arms as hypotheses in some sense. Or each arm is a hypothesis, and we want to find the best hypothesis. It's like finding the best arm. It has the lowest error or the lowest suboptimality. Yeah, maybe. Other than using one kind of math to solve the other kind of problem, I don't quite see what leverage we get from that. But that's a good observation.
Well, in that case, K is the hypothesis, is the size of the hypothesis space.
Yes, like the number of arms, exactly.
Right. This just seems like there's something there. I don't know. I'm sure that if we thought about it long enough or gave someone a homework problem, they'd be able to connect the two.
So just to sum up here, what we've been figuring out is a kind of pack-style bound for these kinds of bandit problems, that we want to say we can get near-optimal payoff after a polynomial number of pulls, or we can get a near-optimal arm after a polynomial number of pulls, or we can make only a polynomial number of mistakes in an infinite run, that all these things actually all boil down to essentially this result. We just have to pull each arm enough times that we have an accurate estimate.
That's pretty good. Well, pack style is better than either monkey style or crane style.
Your monkey style is quite good.
I'm impressed with your pack style.